Hello, I should say buongiorno. Welcome to Research Infrastructure Shaping the Future, Driving a Knowledge and Innovation for Tomorrow Communities. To begin with, we welcome Elena Sgalbi for greetings. She's a Vice Commissioner of the Italy Pavillon at the Expo 2025 Osaka.
Ladies and gentlemen, good afternoon and welcome to the Italy Pavilion. It's for me a great honor today to be here to greet such distinguished guests coming from Italy, coming from all over Japan, in order to exchange views on a topic that is at the core, in my opinion, of the theme of this Expo, designing future societies for our lives. The theme, as you see, is research infrastructures shaping the future. So shaping the future means building new societies able to better fulfill our needs as human beings in a future that is not far away. So I think many of the things we imagine as something happening in the future, they are happening right now. And this is due to the extraordinary advances that our scientific communities have been able to do so far. But science, generally speaking, is also very connected to this Expo theme, also for another region. And I think we are going to learn more about it later on. In the sense that in order to do research, in order to build infrastructures able to tackle very challenging topics, we need an international cooperation. Nowadays, it's impossible, or almost impossible in many fields, to put together the resources, human resources, economic resources, technological resources, without cooperation. I can't imagine something more relatable when we talk about interconnection than scientific cooperation. We think of ourselves more as human beings than citizens of one nation rather than another. And the well-being of the humanity at its core is at the very basis of this kind of research. So I am very honored to welcome once again our distinguished speakers that are going to give us important elements on such an important topic, and I wish you all a very interesting afternoon altogether. Thank you again for being here.
Thank you so much for beautiful greetings, Elena. So my name is Akihiko Mori. I'm a science journalist working for Wageru Japanese edition in Japan. So I'm always consulting intersection of science and humanity. So, okay, so we have two round tables today. I'm doing a moderator today. So let's begin the first round table, Beyond the Present, Fundamental Physics, Technological Innovation, and Reasonable Solutions Empowering a Community, Enhancing Daily Life, and Tackling Future Challenges. So to begin with round table one, we begin with a short time presentation with speakers. The first our first speaker is Sandra Malveci, INFN Vice President. Please.
Thank you, Aki. Good morning, good afternoon to everybody. So, title of my presentation, From Curiosity to Community, how fundamental research can be seen as a longer-term investment for innovation, knowledge, and public good. INFN is the Italian premier institution for research in nuclear, particle, and antiparticles physics. It was founded in 1951. We know that research in fundamental physics, in order to progress, needs to design and implement increasingly advanced experiments at the cutting edge of knowledge and technology. Experience has shown that such innovation often leads to unforeseen applications that deeply transform and impact on our lives. One excellence of INFN is the construction of particle accelerators. We have a long tradition which dates back to the ever first A++ collider, ADA, in Frascati. Why does INFN design and build accelerators? They enable us to explore the laws of the universe. They represent a unique tool for generating comprehensive knowledge, and we know that there is no true wealth without knowledge. They have a deep social, cultural, and economic impact, and they express a great beauty. This is true, at least for researchers. Accelerators have evolved as tools for knowledge and societal development. Here, I just put some pictures of operating accelerator in different fields, in Italy, in Japan, in the Middle East, and I would like to say that Sesame in Jordan is a good example of science for peace. It was built to foster projects to cross divides. And at the end, I see the High Energy Frontier machine in Geneva. In this table, I just details the fraction of the application in different fields. I'm not going to go through it, but I would like to mention that out of the 30,000 particle accelerators now running in the world, only 1% is dedicated to the fundamental research. Medicine is the largest single application, employing more or less 1/3 of all accelerators, and there is a big turnover generated by the construction of the accelerators. Of course, we have to look at the future continuously, and so what's next? In Europe, we are in the thick of the process of the update of the European strategy for particle physics. Europe is designing its longer-term future in order to maintain the leadership that he has in this field, and also designing the future of CERN, which is a center of excellence which has to be maintained. All the skill, counted in all this year needed to be maintained, nurtured, and developed. We work in a context of collaborative agreements, and so CERN and other institutions are working together to design the future of CERN, design for the next machine, but also to integrate regional and non-regional initiatives. The process is performed in close coordination with other countries, because we would like to have the best use of resources globally. So other countries advanced their proposal. We have ILC, the International Linear Collider in Japan. We have CEPC, the Circular Electron Positron Collider in China, and the Muon Collider in the US. An example of synergy that we can have in this field is just the agreement for development, which was signed by Japan and CERN a couple of years ago to foster network for IRC technology. The future machine is FCC. You can see there a design, and you can appreciate how big, how challenging the machine and the enterprise can be. 19 kilometers, more or less, of circumferences. We have a good example also of a bridge from FCC to industry. This is represented by a project that we are carrying out in Italy now, is IRIS, the Innovative Research Infrastructure on Applied Superconductivity. It was funded through the European Next Generation EU funding through the Ministry of University and Research. The physics case is in the fundamental research and is connected with the realization of high temperature superconducting high field magnets for FCC, but it was seen an opportunity to reinforce the existing Italian infrastructures, to create an European excellence center for testing power cables, to train younger people and go on with the expertise and tradition and hiring people. And also, we try to involve industry. We are collaborating with the SAG superconductors to produce a high-performance superconducting cable, which could be used in the next future, to make superconductivity a technology to transport energy with the reduction of losses and reduce environmental impact. In Italy, we have national labs that represent assets for us. In each laboratory, we have a flagship program. So in Frascati, Laboratory di Frascati, we are working on a facility for very high field plasma accelerators, which could lead to compact accelerators in the future, and could help many various community biologists, chemistry, material scientists to perform their researches. And again, it is funded through European Research Innovation Program, and also enlarged by, again, Next Generation EU funding and Regione Lazio. In Laboratory di Legnaro, we are studying nuclear matter in extreme conditions. We produce radionuclides for diagnosis and treatment of cardiac and oncological disease. The infrastructure is at advanced stage of construction. Already in the summer last year, we had some test beamer in operation and produced the first gamma decays of theranostic radionuclide, the copper-67. And in Laboratorio del Sud, in the south laboratories, again, funded by the European Infrastructure Program, we are upgrading the cyclotron, increasing the intensity of ion beams to study rare phenomena in nuclear physics experiment, and the work is in progress. The last slide, before concluding, just to remind that the INFN is collaborating in Japan with Japan-based experiments with accelerator in the precision favor physics. And so the experiment, we are collaborating at T2K, study on neutrino oscillation, CP violation in the electronic sector. Hyper-K, which is a next generation neutrino observer, we have very wide scope, study neutrinos from supernova, the sun, and accelerator beams, and also the beauty physics at Belle 2 a Super KKB, a particle detector to explore the intensity frontier, and probably hadron decays to study CP violation, again, symmetry between matter and antimatter in the quark sector for new physics. INFN contribution in all these experiments go from construction, hardware, commissioning, operation, computing, and physics analysis.
Sandra. Okay, let's move on to our next speaker. We will welcome Ezio Plebitali, INFN Director of the Gran Sasso National Laboratories. So presentation time is 5 minutes. So
I will try to stay in time.
Yes. So if 4 minutes is passed, I raise my hand. So please finalize it in 1 minute, please.
That's fine. Okay, we are talking about infrastructure, and I will try to describe in a few words what is one of the most important infrastructure that we have for scientific research in Italy, but also as a reference laboratory in the world. The Gran Sasso Lab is is located in the central part of Italy and is made of two different infrastructure. One is the external building where we are preparing the technology, we develop the test, we are constructing detector. And the second part is located in the underground, just below the Gran Sasso Massif in the central part of Italy. So in some way we have a laboratory that is located under the mountain in order to guarantee specific condition of operation for our experiments. Why we are going underground? We are going underground because our body now is heated by cosmic ray. In this room we have something around 200 high energy particles per square meter per second that travel our body and give us this interaction directly. But our lives was the human, not only the human, but the life on the earth was generated starting having this condition, and we don't suffer of the radiation that arrive on the earth in this way. But the problem is our instrument. Our instrument doesn't work in this way because the large number of particles generate a lot of interference and doesn't allow us to perform high sensitive measurement. So going underground, we shield our instrument, and in this way we are able to detect very rare events that could not be measured in the above ground. So this is the situation. So we go underground. We have a coverage of 1,400 meters of rock. This 1,400 meters of rock reduce strongly the flux of cosmic ray. We have a reduction of a factor 1 million. In this way, we have a situation in which the number of particles that arrive in the underground is sufficiently low to guarantee that our experiment will be performed in what we call a cosmic silence condition. And obviously, the laboratory is very large. It's one of the largest laboratories in the world, and at the moment is one of the reference laboratories in the world for astroparticle physics. We have an international community in the lab. Just to give you an idea, in 2024, we have 1,300, more than 1,300 scientists registered in the lab, performing measurement and working in order to generate experiment, to make measurement, and so on. And the interesting thing is that if we analyze the period between 2020 and 2024, we published something around 1,000 scientific papers, and we involve more than 75 countries in the world that work with us on these activities. So we are really an international laboratory, and the impact of our activity is very large. We have collaboration coming from from many countries, and we have a strong collaboration also with Japan on many experiments in the past and also in the present experiment that is running in the underground. Just looking inside, you see that this is the configuration. We are full of experiments. We have many experiments that is running, that is under construction, that is under the commissioning. So it's a continuous construction, measurement, the commissioning. There are larger experiments, smaller one. We make the R&D phase in the underground. That is not an easy task because we have to guarantee the access, the safety, the respect of the environment. So there are a lot of rules that we have to maintain. We are in a specific place because the laboratory is installed inside a park, in the Gran Sasso Park, so we have to respect also specific rule in order to guarantee that the lab is working the right way for the scientific point of view, but also minimizing all the impact in that sense. Closing, this is the research line. So we are a reference lab for astroparticle. As I said, astroparticle is our main business, but there are also many other scientific fields in which we are involved in. Geophysics, geology, we are working for support a specific study, for example, for earthquake and seismic analysis. We are working on biology. We have biology underground that is very interesting for the future, also for application in space. And, quantum mechanics, general relativity, quantum processing. So the lab is involved in an application that is not strictly related only to the astroparticle, but also on other fields of the research. I will stop here and I will return to this discussion.
Beautiful.
Okay.
Okay, last speaker, we welcome Naohito Saito, KK Director of the Institute of Particle and the Nuclear Studies.
Well, thank you very much for the opportunity, and hello everybody, possibly connected from Italy right now, I guess. So I'd like to go over what kind of thing we have been doing in Japan now. And based on the accelerator system, accelerator infrastructure in Japan, we have been exploring many directions of the particle and the nuclear physics as a fundamental science. And we are exploring energy frontier, and also we are working about on how the universe is emerged. And we are working together with the astroparticle physics, part, like in the Grand Sasso, a la Grand Sasso type, the experiments together too. So all the background has been explored by the theoretical physics division too, okay? So we will be coming back to this, but why we have been doing this? So we are trying to understand the actual history of the universe, and which being actually written or drawn even like this. And we know that by now, we know that this is the evolution of the universe. And because the 13.8 billion years, it is hard to imagine. Therefore, I divided it into just 4 eras. Most of you know that after Big Bang, how the universe has been developed further. But we divided into 3 eras. So first of all, at the Big Bang, we sort of see the creation of the particles, elementary particles, which is the basis of the many things we have involved. And after that, there's a time that those quarks and the leptons are formed into the form of the atoms and so on, which is, again, the basis of our existing world. And after that, there's a so-called production era. We are making a lot of new things. Among others, life is developed on Earth. So far, it's only the place we found the life itself, but there might be some other places that we may be able to find the sense of the life, okay? But anyway, so even before the Big Bang, there's a time that when the space and time was created, okay? So this is so far the kind of knowledge we have been developing, especially basing on the accelerator system and also the observation of the astrophysics, looking at the universe, okay? So we have been doing all the experiments and the observations and so on, basing on that, and that's all relevant to your daily life and even further future life too, okay? So one of them being, that's been already explained by Sandra, that we have been doing this, the lepton colliders. In fact, the concept of the lepton collider has first realized in Italy, and even this nanobeam scheme we have been doing, it's a really sharp beam colliding together to make the Big Bang to be reproduced on this Earth, is done by the collaboration between Italy and Japan. Okay, so we are really exploring this region altogether. And by now we have more than actually 1,200 of the collaborators from all over the world get together to see how the particles has been created in the creation era, okay? And also we have a proton driver near the Tokai area. That's close to, we're facing on the Pacific Ocean, so it is on the beach. But we have been doing an interesting experiment over there using a proton driver, and one of them being the material and life science facility. So that's related to really our daily life. On top of that, yes, we have been doing a neutrino beam experiment. We are sending the neutrino beam over to Kamioka, about 300 kilometers away. So we have been utilizing this, the production era and the formation era, creation era has been also studied too, okay? So this is the examples of the neutrino experiment, and I think a detail will be explained in that second session by the prominent leading scientist. Okay, so this is just a snapshot of the big collaboration we are doing, and we are really completing the big whole to be finalized soon, in the end of June. Okay? And we are also working together with the European countries at CERN to actually explore the beginning of the universe. Let me move on. And this is probably close to final slide. But by using neutrons, actually, we are able to capture the image of the magnetic field. Okay, so magnetic field you cannot be easily seen, but you're now looking at the rotating fields, and this is only done by the polarized neutrons and so on. This is one of the examples. But having said that, I'd like to say that I think science is the collaboration of all human beings across the space and time. So none of these things has been happening due to one single person, but this is done only by the all people over long years. So let's work together and condividiamo più emozioni. Okay.
Thank you so much.
This has to be okay.
Okay, shall we begin the talk session? Oh, the discussion phase. So, thanks so much. So, I'd like to kick off the talk with KEK. As we saw from your presentation, Saito-san, so KEK is a major institute managing important infrastructure and cutting-edge projects ranging from accelerator physics to neutrino physics, from material science to technological applications. What project KEK currently focusing on, and what are the scientific and strategic goals behind them?
Okay, that's a very important and very difficult to answer that kind of questions. And we are really exploring the three major areas. One of the area is actually the Bell 2 Super KEK-P experiment. We try to create the beginning of the universe on the laboratory. That's one thing. And another thing is the neutrino experiment. Yeah, we have been exploring together with the similar technologies as the Grand Sasso's doing. And the other one is the LHC experiment, where there's really the highest energy on Earth can be actually emerged on that experiment. So that's the major three areas. But those are really large-scale experiment. And actually basing on that, I think more important thing is that we are developing a future, like a shaping future based on these technologies. So we are gathering new ideas to explore the frontier further, especially combining new technologies, including the quantum technologies and so on. I'd like to say that's the main thing we are doing. By doing that, actually, even existing technology or experiment can be improved further. So those has to be, go together. The exploitation of the current things and the exploration of the future things has to go together. So I think that's the, kind of the thrust we are trying to create, in our laboratory. Okay.
Thank you. So today we don't have a Q&A session, but we are always open to questions. So if you have any question, please raise your hand and give me any question. Thank you. Okay, how about investment strategy in Italy? I'd like to ask Sandra. Large research infrastructures are also defining elements of INFN, through which it has plays a key role in the history of particle physics in Italy. Today, the Institute is investing in the enhancement of many of its infrastructure and in the creation of the new laboratories. Thanks also to NRPP funds. I don't know the pronunciation in Italian, but NRPP funds allocated by Ministry of University and Research, as well as regional funds. Yep. What is your investment strategy? Which sectors are you focusing on, and why?
Thank you. PNRR, Piano Nazionale di Ripresa e Resilienza.
Thank you.
Okay. Nothing. Okay. Well, our investment, thanks to this investment from the EU and the ministry, actually aims at strengthening the international role in science that our institute has, but also in advancing technologies and contributing to the development of economic and territorial development. They align with the priorities that we have in our national research plan and in Europe. So, for instance, the digital transition and the green transitions. And we work to modernize our infrastructures, of course. So our laboratories, one case, which maybe will be mentioned by Ezio, is just Gran Sasso for future. The idea is to have a global hub for underground physics for next years. Another example is the superconductivity that I mentioned before with the IRIS project, which is linked to different laboratories and expertise all around. In general, what we are doing is to maintain our fundamental research, but also focusing in emerging technologies, quantum technologies, artificial intelligence. We don't have to forget that we also are investing in a national research network and in a center of excellence for big data, quantum computing, and high-performance computing, which is important for digital sovereignty of Italy and Europe. And once more to mention is the KM3NET, which is an experiment for high-energy cosmic neutrinos, which is linked to Laboratori del Sud and the south of Italy, and the ETIC infrastructure, which is to study and to foster the Italians' bid to host the new gravitational wave interferometer Einstein's telescope. So this is the general view.
Thank you. So if we want to add questions, please. It's okay. Oh, thank you. Yeah. Right. Not only accelerators, there's another field in which both Japan and Italy are at the forefront of research, neutrino physics, I think. So I'd like to ask Ezio, the INFN and Gran Sasso National Laboratories are the reference currently operating underground facilities for astroparticle physics, as you mentioned. Some of the leading experiments in this field for dark matter searches or neutrino studies are there. What research activities are currently underway, and what are the upcoming major projects of the laboratories?
Okay, so you mentioned two important fields. One is neutrino physics, and the other one is dark matter search. So for neutrino, the point is very clear in our opinion. We have a particle that was proposed just as a story in 1930, for the first time, and was encapsulated in a theory by Fermi in 1934. But if we look to the particle, we know only some of the characteristic of the particle. So this particle remains something unknown for many points of view. And one of the main issues that we have now for neutrino is to try to characterize the neutrino in all the aspects. So this is something that is an important issue for the research, not only for the Gran Sasso, but also in Japan, in many other countries. We are trying to spend effort in order to understand what is the real characteristic of the neutrino. So in Gran Sasso, we closed the period of what we call neutrino from the sun. We stopped the Borexino experiment in 2021. It was a very great success in Italy because in Gran Sasso we have a lot of measurement that was able to demonstrate what is the real operating condition of the sun. So in some way, Borexino was a great success because it was able to measure all the reaction in the sun, demonstrating what is the engine that produce the energy in the sun and that allow the life on the Earth. That is not a negligible aspect. In our opinion, this research line now is closed, and we are moving forward for the next step. The next step will be, in our opinion, to try to understand if the characteristic neutrino-antineutrino, and we are looking for double beta decay experiment in the present experiment in the future. So neutrino-antineutrino, the beta decay search is something that could demonstrate what will be the symmetry in the matter and try to understand why when we look to the universe, we see only matter and not antimatter. That is an important question because in our opinion, the matter and antimatter has to be symmetric, but we see only matter, but we don't see antimatter. If double beta decay will be measured, the neutrino-less double beta decay will be measured, we could in principle demonstrate that this asymmetry comes from specific processes, that will violate the symmetry of the particle physics in general. So at the moment we have two experiments that is running. Quarry is one experiment, Legend 200 has different technology, but is in two important experiments at the moment. For the future, we are looking for the new generation. We are discussing new generation experiment of beta decay that will be prepared for the near future. So there are many things to do, but we have no time. But this is a very challenging activity because we are looking for experiment that will be developed in the next 10, 20 years and will imply a lot of involvement from many different countries and many different laboratories. Last point that you mentioned was the dark matter. So what we know now is that our material, what we see in looking to the universe, is only the 5% of the total material of the universe. So what we know is that when we look to the star, to the planet, this material is only 5% of the total. We know that almost 27% of the material is dark, so it's not as we expected, and 68% of the energy of the universe is dark energy, is very far away to understand. So first of all, we try to understand what is dark matter. So in Gran Sasso, we have many experiments. At the moment, we have 7 experiments that is trying to measure the dark matter, look into the possible interaction of this particle with our detector. We are leading in that sense because we have the large number of detectors of this type for dark matter, and also because we are trying to prepare also the future. At present, we are running experiment using noble gas, cryogenic noble gas, xenon, and for the future, we are preparing a new generation that is made on argon detector, as a dark side that is a huge detector containing a large amount of argon material. That is a difficult challenge because it's not an easy task to perform, but it's something that we hope could be helpful for us to understand what will be the real configuration of the dark matter in the universe.
Thank you. This is my curious. Dark matter is a huge theme, a huge question to our humanity. So how much do we know about it scientifically? When do we measure it or evaluate it in the future? In your opinion?
The problem of dark matter is a complicated point because so what we know is that if we look to the galaxy or cluster of galaxy and just looking for the gravitational situation, the rotation that we observe is not does not respect to the rule of the gravitational law if we don't introduce extra matter. But this extra matter is not visible, so we don't see this matter as a matter of coming from stars, for example. The question now is that what we suppose is that the dark matter is made by particles that normally does not interact as a normal particle that we observe in the universe. But in principle, we can also make a different approach. Say, okay, we have the Newton law is not correct. We can modify the Newton law and try to adapt the Newton law to the rotation of galaxy, is another question. So from my point of view, at the moment, it's very difficult to imagine, as what we know now, it's very difficult to imagine that the dark matter does not come from exotic particles. In my opinion, there are rooms to improve the research on the exotic particle, trying to understand if this particle is the source of the dark matter. Then, after the next generation of experiment, if we don't find nothing in the next generation experiment, we have to think about if it is important to proceed in this direction, or try to change attitude and to look in other possible solutions.
Thank you. Okay, let's move on to collaborative community. So I think the keyword of this roundtable, one of the keyword of this roundtable is collaborative communities. So the discovery of the Higgs boson in 2012 was an outstanding international collaboration, including Italy and Japan. Isn't it, Sandra? Yeah. At the ASC Accelerator at CERN, an achievement in which both Italy and Japan played a major role, the theoretical framework of the standard model, a theory that works extremely well and has received countless experimental confirmations over the years. However, it still leaves some fundamental questions unanswered. At the same time, the LHC is nearing the end of the scientific activity, and it's preparing to make way for its upgrade project. It's called High Luminosity LHC. But we know that particle physics works on a decade-long scale when planning its infrastructures. So this is the question. How is the European particle physics community organizing itself?
Okay, thank you. The discovery of the Higgs boson was really a big success of the communities and the standard model of particle physics. But we know that there are still many open questions. Some were already mentioned by Ezio and by Saito, dark matter and asymmetry, matter-antimatter asymmetry, but there are also many theoretical open issues I'm not going to bother you about. But this means that we need to go on and advance our understanding of particle physics and interaction mechanism of this particle. For doing it, we need to think now about the long-term future. So after the LHC, we have to think now about the next project. And the next project, as I mentioned before, is FCC. Which has been, the flag project is FCC, and it was decided in continuity with the previous recommendation of the strategy process, and it was subjected to a very careful feasibility study. And it is a big enterprise, of course, and we need to have the community with a larger consensus. And so Europe is performing now this strategy of particle physics, which is a pivotal initiative to engage the communities to decide together how we have to go on. And last year, there have been many meetings in a national contest to have, really the basis of the community with us. There are inputs now, and we are analyzing all the inputs, which will be discussed and debated in an open symposium that we are organizing in Europe, in Venice, actually, next month. And then there we will decide about the next project, the balance between the accelerator and non-accelerator projects, and the funding, of course, the R&D that we have to go on performing with computing, detectors, accelerator, new technologies, and also we have to decide how to train and how we invest on human resources, so training new younger people, of course. So that's the idea of where we would like to go.
Thank you. By the way, this... sorry.
Yeah.
We are gathering at the actually Venezia next month. To come up with the European strategy for particle physics. And Venezia is, of course, nice place to gather people.
Yeah,
So you have a really
thank you.
good advantage to do that.
I'm quite busy in
Yes.
organizing it. But your intervention also remind me that I should point out that, and I mean, I already spent a word about that, but everything is done in closer coordination with other countries. I mean, even in the group which will draft the final recommendation, we have, of course, a European member states representative, but also observers from non-European countries. So we have observers from Japan, from the US, and so on and so forth. Again, it is exactly the idea of the global collaborative agreements,
Yeah,
which is very important when we are talking about the large infrastructures.
Yes. In Japan also, we have a committee-based discussion is ongoing
Yeah.
to develop the future planning of the particle physics and the nuclear physics.
Yeah, exactly.
So that will be, of course, represented at the
Yeah.
meeting at the Venezia.
Yeah,
Yes.
exactly.
Yeah.
And Japan and US they do the same. I mean, they have this project, this process for defining the future. Yeah,
So it's really global efforts.
Yeah.
Yes, yes.
to make a
Global effort.
consensus. Yeah.
So, Saito-san, could you explain a bit about the community you mentioned?
Okay. Yes. I think
Japanese community.
yeah, within Japan, I think we already we have about 1,000 of the particle physicists and about 1,000 of nuclear physicists, and they are working together as university-based or maybe laboratory-based. Okay, and basing on that, we have a future planning committee, which is a kind of standing committee to discuss about. Conclusion is important, but also the process is very important. Therefore, we have been studying various possibilities, and we're gonna look at the future to even the possible new technologies in the future may help to not only our community, our physics, but also the society. Therefore, that's the kind of the direction we have been seeing. But so far, we have not really concluded yet. But there's a certain directions we are exploring. Yes, that was represented too. The three major directions we have been doing under our lab too. So,
Thank you. And let's take a look at the Grand Sasso National Laboratories, right, ATO. So the Grand Sasso National Laboratories are infrastructure not only for fundamental research, but also for technological and applied research. So I have two questions. In which sectors has fundamental physics research brought the greatest benefits? And second question, and what are the main technology transfer projects that the Grand Sasso National Laboratories are involved in?
Okay, so we have to start to one point, in my opinion, first of all, and that we are preparing experiment. We discussed a little bit this point today. And to perform such a very high-sensitive experiment, we need to develop a cutting-edge technology. That's the relationship between technology and basic research science. This implies that we have to work in order to develop a technology that is normally not on the market, so we need to develop technology and try to work in this way, not only alone, but in collaboration with companies. So there is a strict relationship between the laboratory and companies that works in order to create new technology that could be useful, first of all, for the experiment, but in parallel, many of these companies learn what we discuss, what we prepare for the experiment, and try to transfer this knowledge to their business. That is a direct technology transfer that we do directly working with companies that collaborate with us in developing cutting-edge technology. This is the first point. The second point is that we train people, we strongly train people, and training people in technology means that you are trying to transfer to the young people information and many other aspects that could in principle help the young guys to move on, not only in academic environment, but also in application. I would like to mention, you asked what is the technology in Gran Sasso. I would like to, there are many young people here, so I would like to remind a situation that was in the past. There was a young PhD student that works in Gran Sasso 20 years ago. And
Does you?
No, I'm a little bit older in that sense. And he was involved in manage of data compression, data management and compression of data. Now this guy is the chief of the most important broadcasting company, TV broadcasting company in the world. It was not from Italy. Okay. And when we ask him what is the situation, what he said is that he learned in Gran Sasso the way to manage the data, and then he transferred the information to the TV broadcasting company, and compressing the data, they are able to send messages with the correct rate of data transferred to the communication. So this is a clear example in which we have technology developed in a lab for a specific experiment, but that will be useful for the future. Turning to the actual situation, the situation is that we are working on many technological effort. For example, we are preparing for the side something around 20 square meter of silicon PM. There is an unprecedented technology that we are to prepare, because this will be a big detector able to look to the light, able to detect a single photon that arrives from every sources. So we are talking not to the sensor of our mobile phone, but something that is able to see one photon over 20 square meter of surface. We are working, for example, in collaboration with space company for new material for space. In 3D printing, we are developing 3D printing application for our experiment. This application could be useful also for space application, and we are trying to transfer the information in this direction. There are also applications in cryogenics. Now everyone is talking about cryogenics for quantum computing. The story begins when a Quark experiment realized the big dilution refrigerator for double beta decay experiment in Gran Sasso. It was the first step that now is translated in new application, new cryogenic system that is moving for application like quantum computing, quantum sensor. There are many other aspects. I would like just to be brief, to report one situation in the INFN, not in Gran Sasso, but is an indication of the importance of science, basic science, with respect to the application. There was a there was a researcher in INFN that is working on the quarks dynamics. And they discovered that the application of quarks dynamics could be applied also for molecule, and in particular for proteomics. They decided they move from basic science, physics, to biology. That is now one of the most important startups in the world looking for drug discovery. Just starting from the basic science, we support them in order to proceed in this way. And now this is an important company that is able to promote drug discovery in order starting from the basic science things. And just to mention, they was the people that demonstrate the way in which the COVID enter in the cell using the ACE2 protein. That was an important information for vaccine and so on. And with them, we said, okay, you are discovering these things, but you have to distribute this information to all the world. And we have done these things directly, starting from the activity in the INFN.
If you want to ask a question.
No.
Okay, sorry. So this is just my curious. So now you refer to collaboration with the company and research infrastructure. So regarding to quantum computer, do you have any ideas or any example of collaboration in your research field?
With companies?
Oh, yes.
So our collaboration with companies, yes, for quantum computing you're talking, or in general?
Quantum computer.
Quantum computing. No, okay. For INFN, at the moment, the INFN and Gran Sasso Lab is involved in the program, in US program for quantum computing. INFN is the only institution in the world that is now collaborating directly by the US for their program in quantum computing. This is connected by two things. The first one is that they are interested in cryogenics, as I mentioned. There is a second point that is important, that is Gran Sasso Lab is shielded, as I showed before, is shielded for the cosmic ray. And one of the reasons why the single bit could be changed the status due to the interference could be generated by cosmic ray. We demonstrated that the absence of cosmic ray could help the quantum computing in order to be more stable for the point of view of the communication. So in that sense, we are collaborating with IBM in this group with the US. We are collaborating with a company in Germany that is developing the single chip, trying to analyze what will be the best configuration of the single bit, cryogenic single bit for quantum computing. But Gran Sasso is also working on quantum sensor because a large part of our cryogenic sensor is made using a very sophisticated sensor that is now applied for our field of research, but is directly applied also for quantum sensor in general. For example, we are able to measure with our sensor the limits, the quantum limits in the detection of a single event. And this is something that we are promoting with some company. So we are not producing the single bit. We discuss with the company, they prepare the single bit, we test the single bit, and we indicate what will be the possible solution on some problem that we experience during the test.
Can I
Please.
quickly add something? In the context of the Next Generation EU funding, we also, as I said, we have a national center for big data, quantum computing, and high-performance computing. And there is, what is interesting is that there is a mixture of research institutes and private companies. And the idea is to have all the different flavors of the competencies and skills that try to trigger one each other. So even many new ideas of application or something for us can come from and to the industries.
Yes. I think it is really amazing that we really share the same backgrounds that are regarding also the quantum computing and the cryogenics and the also, I think microstructure, microelectronics is one of the things we have been exploring. But when you look at actually the quantum computing, it is hard to imagine that the general purpose quantum computation can be done in the foreseeable future easily, right? Therefore, the quantum computation results has to be communicated to the modern or maybe classic computing infrastructure. Therefore, there's a large scale of the data has to be transferred. Data transfer has to be happened. So that technology is also similar to the case that what we have been doing for the large-scale experiment we have been doing. Yeah. So that part is one of the things we have been looking into. And actually, we also started the collaboration with the Toyota and other companies, especially looking into how the possible small-scale computing, quantum computer can be transferred to the normal life technologies. Yeah, so we are talking about a really, really low energy, low temperature, the quantum scheme only, but some of the technique can be applicable maybe in the not too low temperature, but daily life temperature as well. So that's a direction sort of we have been exploring. Yeah.
Just to make the last comment, one of the main issues in the quantum computing is that the capability for quantum computing is strongly linked with the capability to write down the correct software, the correct codes. And this became, in time by time, specialized. One of the main issues that we have now is that we are trying to understand what will be the best approach in order to prepare the code to be applied as wide as possible. Because, for example, now there are we have collaboration on codes, for example, with pharmaceutical company, the drug producer, because in biology, the quantum computing could produce a very strong input, but it became very specialized. In this way, it became only related to a relatively small sector that is not useful to make a large expansion of this type of technology, because you need to have a wide application, otherwise very difficult to proceed in this way.
Thank you. Okay, I think we are closing this session. So this is the final question. So we can think of research infrastructure as a resource hubs, resource hubs capable of attracting, organizing, and expanding them, of catalyzing innovative processes, and of giving value back to scientific communities. To industry, to economic system, to the territory in which they are, and to local communities, to countries, to societies in the broadest and the fullest sense of the term. What can be done globally to best enhance the role of research infrastructures?
Yeah, this is a very important question.
Yes, a huge question.
It's a huge question. I mean, as you might have understood from the discussion that we have now, the high energy physics community is already organized globally. So there is already a cooperation among in different countries. And I think that the only way actually to make the infrastructures working well is just to foster cross-border partnerships, creating networking with national, regional infrastructures, trying to assess standards for facilitate interoperability, for instance, data sharing. This will be very important for medicines, for instance. We have to embark less developed countries, underdeveloped countries, and so for that we need to implement digital platforms. We have to create any remote access models for overcoming barriers, and we also can try to use these infrastructures embed infrastructure in science diplomacy. I already mentioned before the case of Sesame in Jordan. This is a nice way to make infrastructures even more internationally more appealing. And there is a point that I would like, 2 points before concluding. One is, of course, exchange again human resources, programs for exchanging students, for also staff people could be very useful because they have to go and use infrastructures. And communication. I think that it is really very, very important to promote an effective communication toward the society, because people have to understand how important large infrastructures can impact on their daily life. I already tried in the beginning, the introduction, to say something about that. But we have to make people aware on how they can be affected by this infrastructure positively. Okay, so communication is a point that I would try to foster. So coordination, strategy, global efforts. These are the key words.
Thank you. Can you add some comments following?
Yeah, I think what Sandra says is really true. That I mean, I think on top of that, probably any research infrastructure have its own goals and so on. But I think people's strength is that we can really go beyond even the original goal. So research infrastructure is a really infrastructure, like a platform of the maybe SNS or something. So that's a really platform to actually develop the future together, the shaping the future. Yes?
Yes.
Yeah. So that's the role of the research infrastructure. And probably, if I could add, that any of the science being done there is not to be done by the single person, not by the only one country, and not at the, being done at this, one day even.
No.
So it is really, what I tried to mention during my talk, that it is really collaboration across the space and time. For long years, we have been really creating this atmosphere to collaborate together, and that is really specific about the science, I think. Yep. So that atmosphere has to be transferred to the other areas, so that we can really collaborate all together. The science result is not to be utilized for the one side, but it should be really utilized with both sides globally.
Yeah,
Yeah.
exactly.
Yeah. So, thank you.
Just to add, to reinforce this point, looking as a responsible of a research infrastructure, if I look to the future, what I see is that the experiment is increasing in complexity, but also in cost. Yeah. So we have to invest a lot of resources in order to prepare the future. And what is important is to minimize the dispersion of these resources. So the collaboration, the global collaboration, is not something that we have to put as a possibility. Is necessary because it's the only way in which we are able to minimize the dispersion of the resources, try to collaborate on the item that each other could be, we could develop these things in order to maximize the result at the end, because we can share our information, try to support the development, and trying to maximize the use of the resources that we have now. Yeah. Because we are not in a condition of infinite resources. We have to consider also this point.
Just to say, funds are absolutely needed, mandatory. I took for granted that anyway it was already implied. But this is also the reason why I think the effective communication is important, because people have to understand why they are paying for research, for large infrastructures, and then we can do our part. But then it will be the first step.
Thank you so much for brilliant ideas and the collaborative mindset we're closing this session. Thank you so much.
Thank you. Thank you.
Okay, so let's begin next session. Roundtable 2, exploring new frontiers, how physics unlocks the secrets of the universe and expands the human understanding. So at the beginning, we call speakers for a presentation, the 5 minutes presentation. So first speaker is Marco Pallavicini. Welcome.
So thank you. Good afternoon and good morning in Italy. I will focus a little bit more on the astroparticle physics activity at INFN. My colleague Sandra Malvezzi have spoken before about INFN, especially in particle accelerators. Here I focus on a second, let me say, leg of our activity. INFN is called Istituto Nazionale di Fisica Nucleare. The word nuclear physics has a kind of historical meaning, but the activity is very broad. We have 5 big sections that we call commissions, one devoted to particle physics, number 1, one devoted to astroparticle physics, number 2. We have a third on nuclear physics, a fourth on theoretical physics, a fifth on technological research, which we have covered a lot in the first round table. Now I want to focus on astroparticle, which is another important item with which, together with Japan, we work a lot on many aspects of research. So what is astroparticle physics? It's the study of fundamental laws of physics, essentially by using natural sources of particles coming from space. A long time ago, the research was started with cosmic rays. Then we learned how to detect photons of very different wavelength, high energy photons, and then neutrinos. Neutrino astronomy, as was recalled, essentially was born here in Japan in 1987 with the detection of neutrinos from supernova 987A. And then we have another source, which is gravitational waves, discovered 10 years ago and now becoming more and more important. And of course, we dream of another source, which could be the direct detection of dark matter particles, which will happen sometime in the future. We don't know when. This is a short summary of the main activity in astroparticle physics at INFN. We detect the solar neutrinos with Borexino. We will do it with Juno. We will do it together with our Japanese colleague, of course, in Super Kamiokande that is still running, and Hyper Kamiokande that will come soon, and then in Dune in the United States. We look for high-energy neutrinos using underwater detector, especially the ORCA detector near France and the ARCA detector near Sicily, which are both devoted to the study of neutrinos, either coming from the atmosphere or coming from deep space. We study cosmic rays in Auger in Argentina. We study high-energy photons using detector at the Canary Islands, and in the future, again in Chile, with the CTA detector. We look for dark matter. We haven't found it yet, but we look it underground at the Gran Sasso Lab. We heard a lot in the previous round table, but we also look at the dark matter indirect signals from space using satellites. For example, AMS-2 is running on the space station, and the GAPS detector will be launched in a balloon very soon. And then, last but not least, very important, we have the new field of research, which is gravitational waves. Virgo is one of the detectors running in Italy, one of the 3 detectors that detected gravitational waves so far, but very important, Cabra will come soon, and we hope that very soon we will start working together to improve the capability to detect this very important messenger from space. Just a few words about these 2 main lines, neutrinos and gravitational waves. We are very much involved in developing this ARCA detector, which is becoming the first neutrino telescope underwater, fully devoted to the detection of very high energy neutrinos from space. And then ORCA, which is the follow-up of the previous Antares detector, which is mostly devoted to study of neutrino oscillations using atmospheric neutrinos. These 2 detectors are both being constructed in collaboration with CNRS and NICEF and other European countries, and of course is one of the milestones of astroparticle physics at INFN. Here, I just mentioned very briefly, this detector has detected the highest energy neutrino ever detected by human beings. It's more than 200 PeV, which is a fantastic energy. We don't know the origin. It's truly a mystery, but it's a fantastic opportunity to improve our knowledge of the cosmos. And I'm closing saying a few more words about gravitational waves. Our main detector is Virgo, which is currently running with a sensitivity of about 55 megaparsec, which is taking data together with LIGO. We plan to improve it. There is a strong debate so far in progress to study what kind of improvements we can do in the next year, upgrading the detector in stronger collaboration with LIGO and CAGRA in what will become the IGWN collaboration. Of course, Virgo will be a main partner of this in the next year and will continue to take data until the beginning of Einstein telescope. And last but not least, I conclude my talk saying that, of course, our dream for the future is to build a next generation gravitational wave detector underground in Sardinia, which is called the Einstein telescope. The connection with Japan is very important because our Japanese colleague started before us to the adventure to build an underground cryogenic detector, which is of course a very difficult task, but of course with which we work together, we collaborate, and we have a lot to learn about the problems connected to cryogenics, which will be very beneficial for Einstein telescope. Our government has made a commitment of 1.3 billion euros if the detector will be built in Sardinia, and we already invested 50 million in R&D. So this is, of course, one of the milestones of our research, and of course, it will be the future of astroparticle at INFN and in Europe, I would say. Thank you.
Thank you so much, Marco, and INFN Vice President. Okay, we welcome next speakers, Emilio Ladicioni, INFN and Chair of the Hypercommunicante Institution.
Okay, so good afternoon. I was asked to present to you what are essentially the scientific goals and what Hypercommunicante will be able to tell us. So I will start with a brief introduction on what are neutrinos. So they are elementary particles. Among the elementary particles we know are the most elusive. They can travel across the Earth many times, thousands of times, without interacting. Their mass is so small that it was considered for a long time to be zero. Actually, we know something about the mass. We know the mass difference between the masses of different kinds of neutrinos. We know 3 of them. And we know an upper limit of the mass of one of them. So we can find neutrinos in several places. First of all, in cosmic rays, as we have heard already. Coming from stellar objects, this is an image of the sun taken by looking at neutrinos by Supercambiocande. Or we can produce neutrinos using accelerators. So regarding neutrinos, here in Japan, there's a fantastic infrastructure spanning 300 kilometers, starting from Tokai in the Baraki Prefecture. This is the J-Park laboratory. It is able to send a neutrino beam all across Japan, east to west, to the Kamioka district, where today you find Super Kamiokande, and tomorrow Hyper Kamiokande. Now, why are we looking at neutrinos 300 kilometers away? Sounds funny. This is why, while they travel, neutrinos are able to show a peculiar behavior, which will help us shed light on one of the mysteries, which is why today in the universe we do not observe antimatter, while we know that back in time, closer to the Big Bang, we suppose there was equal amount of both. So how do we use neutrinos to try to understand this? So while traveling, the 3 types of neutrino behave, let me say, sort of coupled oscillators. I mean, while they travel, they are able to change themselves one to the other, and they do this with repetitive patterns which look like sound wave beatings. So the closest thing I can think of in everyday life is, if anyone knows how a piano works, you have notes made by 3 strings, and if you play with tuning the strings, you hear beatings. And this is also formally the same kind of things happening here. So this phenomenon is already well established with a prominent contribution from T2K and Super Kamiokande. What is interesting is that this allows us to show if matter and antimatter behave in different ways. So what are we looking for here? So matter and antimatter is something you can treat as one of the mirror of the others. If there is perfect symmetry, they behave the same. You do the mirror operation and you find no difference. Everything is mirrors as you expected. Try to mirror a left-hand drive car to a right-hand drive. Not everything mirrors, the pedals do not. So we are trying to look for something of that kind. I mean, if you change car from one to the other, you are puzzled because not everything changes as you expect. And this went to a very famous journal on the cover page. So we produce neutrinos and antineutrinos. We observe them at the distance. And Hyper-K will have the required precision to go to a real discovery. So establish the effect, if it is there, and prove it once, forever. So how do you do that? Well, you build on the knowledge starting from Kamiokande, then Super Kamiokande now, and this is the huge size Hyper Kamiokande being constructed in this moment. Few numbers, from 4.5 thousand tons of water to 260,000. And a brief recap of the amount of success of the two previous experiments compared to Hyper Kamiokande. How do you do it? You observe light in water. Particles in water produce cones of light, something very similar to what you see when a duck crosses a pond. The duck goes faster than the propagation of the waves it creates. It's about the same kind of phenomenon. So you place yourself underground, you fill a cavern with water, and you line the cavern with photosensitive elements and detect the light produced by particles. By the way, constructing by subtraction, I mean, doing things by subtraction is an interesting philosophical and an interesting philosophical concept. In addition to this, this is a great opportunity for community building. The experiment is hosted by University of Tokyo and KK. It counts about 600 members with institutes from almost everywhere. There's a large community coming from Europe, supported by the European Union through a number of grants, which allows us to have scientists present in Japan for a relatively long time. Funds are secured for the next 3 years of construction, and INFN here is the driving institution. So summarizing, Hyper-K will bring us a better understanding of several interesting and puzzling phenomena, among which matter and antimatter asymmetry, better limits, I did not discuss this, but limits on proton decays, and it will work as an observatory, an astrophysical observatory, contributing to multi-messenger astrophysics. And it is a unique occasion for long-term collaboration and strengthening connections between different communities. Thank you.
Thank you so much. All right, we will welcome last speaker, Hisaki Shinkai, Osaka Institute of Technology and Kagura Collaboration.
Thank you. I'm Hisaki Shinkai from Osaka Institute of Technology, and I'm very honored to be here. And today I will introduce about the gravitational wave physics and astronomy, and also introduction of the Kagura project. So Albert Einstein made a general relativity more than 100 years ago. And he predicted the existence of a gravitational wave, which is the wave of the space and time traveling to the light of speed. And he predicted, but 100 years we need to spend to actual detections. So actual detection was appeared in 2015, 10 years ago. So I prepared the slide for the general people. What is the general relativity is? Einstein's idea of the gravity is like space and time is like a bending, like a trampoline's membrane. So if the massive object is here, here, then the membrane will be spending over, and the small object will be coming to the of this large mass. In the universe, more than 50% of stars forming the binary, two pairs of these stars. So suppose the two boys grabbing each other and running about over the trampoline, then there will be wave will come. So gravitational wave detection is such kind of project. So in somewhere in the universe, black hole binaries or neutron star binaries will be merging due to the gravitations. And if it happens, then wave will be appeared and it travels to the universe. And if we have a very large interferometer, laser interferometer, then we can search such kind of passing of the gravitational wave. That is the idea of how to detect the gravitational wave. Actually, we need to fight with the noise of the detectors. So in the world, near Pisa in Italy, European group has a Virgo detector. It has a 3 kilometer arms here. In Japan, we have a Kagura. We have also the 3 kilometer arms under the mountain. And America has 2 detectors. So international collaboration is crucial. It's necessary because one single detector cannot declare we observed the gravitational wave. 2 or 3 detectors simultaneous detection is necessary to say we detected. And from the gravitational wave detections, we will learn many things from the waveform. For example, we can learn about what is the source parameter is, what is the mass, or what is the spin of the object. And also from the waveform, we can check how much Einstein's general relativity is right. And that will be crucial for advancing the physics to the next generations. So far, we have more than 90 events of the binary merger of the binary black holes. So this is an image, not in the real scale, and actual wave is only for passing 0.2 second, for example. But such kind of many detections are now ongoing. So Kagura is constructed underground, actually in the 200 meters below in the mountain, because the Earth is always vibrating, and we knew that the underground is more, we can save the seismic noises, vibration of the noises. And also, we are going to the cryogenic technologies, because we are using a laser power is increasing, then the mirror will be heated. So we need to go into the low temperature, like a 20 Kelvin, minus 250 degrees of freedom. So such kind of advanced technology requires for us to 10 years to develop. And we also have the fighting with much snow in the winter season, like here, 2 meters depth. And also we need to fight with the bear. We need to wear the anti-bear bells every time. So anyway, we are going to such kind of technology. And also we are now spending the collaboration with the LIGO, Virgo, and Kagura, and more than 5 years collaborations. And from the next month, June, to the end of this year, we are continuing the actual observations. And we are now going to the more than 200 detections for the past 2 years here. And also for the general people, every time we are publishing the paper, we are making the science summary, introducing 2-page summary for general people. So if you are interested in, please check the pages. So in the multi-messenger astronomy is a word to the many astronomy detections collaboration together. So the astronomical observation starting from the Galileo Galilei 400 years ago with the visible light, and so the astronomers developing the infrared, radio, X-ray, gamma ray. I forgot to mention about the neutrino. And finally, we have a new eyes of the gravitational wave. So this is, we say, multi-messenger astronomy. So in the many bands of the light, we are seeing the object simultaneously. And we will see more new features in the universe. This is my final slide. So Italian and European groups are now developing the idea of the next generation of the Einstein telescope. So 10 kilometers triangle shape of the laser interferometers. And as Marco explained, this will be planning to underground with the cryogenic technologies. And Kagura can contribute to work with you. So that's the end of my story. Thank you very much.
Thank you so much. Okay, so kicking off the talk session, we begin with Kagura, so which means Shinkai-san. Okay, I ask you the question. So the discovery of gravitational waves has opened a new observational window on the universe, as you mentioned, and Marco also mentioned too. So how crucial is global cooperation in this scientific endeavor? And what is Kagura's strategic role to this?
Okay, so as I mentioned, only single detector cannot declare we observed because always the data is crazily noisy, and actual wave size is inside of the noise. So we have something like simultaneous detections using the some statistical techniques are necessary. So in that ways, more than 2 or 3 detectors are required. So that if Kagura joined as a fourth detector, then our parameter search will be more clearly. For example, from which direction we can see the source of the gravitational wave. Such kind of the detailed parameter estimation will be helpful for the astronomers. So the Kagura's joining is really, I believe, contribute to the astronomy. Actually, Kagura has not yet detected any gravitational wave signals yet. And but from this coming 2 weeks in June, we start with a 10 megaparsec scale, and we see together with Virgo and LIGO, we believe we can have the simultaneous detection, actual detections. That is the exciting era for us. That is our current status.
Thank you. So we are moving on to Super Kamiokande project. So I'd like to ask to Emilio. Yeah. Not only gravitational waves, but also neutrinos, as you mentioned. Invariable cosmic messages capable of carrying unique information about their sources all the way to us. So you work here in Japan on the Nobel-winning Super Kamiokande project, and on its successor Hyper Kamiokande you mentioned in the presentation. So what technological innovations will Hyper Kamiokande introduce, and with that objectives? And what contribution will Hyper Kamiokande makes to multi-messenger astronomy and neutrino research?
Okay, there are 2 parts in the question. The first is
Yes.
which new technologies will adopt for Hyper Kamiokande.
Yeah.
And the second is what is the contribution to multi-messenger astronomy, right?
Yes, please.
So Hyper Kamiokande will represent a technological challenge on many respects. Already in Super Kamiokande, to give you an example, Super Kamiokande is the place where you find, I guess, the purest water on Earth. So you need perfect transparency to make sure that the light you create in the water is correctly received by the photosensitive elements. And this requirement will be even more important to Hyperkamiokande given its additional size. And the water is so transparent that someone having stood on the boat inside the cavern told me that you see the bottom as there was nothing in between, right? So then in Hyperkamiokande you will have additional kind of photodetectors. You know that this family of detectors are using photomultipliers, very large photomultipliers produced by Hamamatsu, which have been improved from one generation to the other, and we are going to use the most sensitive produced so far. But in addition to those, we will have a few, where a few means, given the number of 2,000 Hamamatsu photomultipliers, a few means almost 1,000, what we call multi-photomultipliers. These are units the same outside size as the Hamamatsu ones, but with inside an array of smaller photomultipliers. And the advantage of these is that they will give additional, better time resolution and the possibility to intercalibrate the two different type of sensitive elements. So calibration in Hyperkamiokande will be key to lower the minimum energy which we define as observable. So calibration. Then, of course, Hyperkamiokande will produce a lot more data than Superkamiokande. So this implies proper electronics data acquisition system, and I expect that the role of using words escape me, machine learning algorithms will become more and more important. So I expect the developments in that kind of field, which is nowadays common in the large experiments which have to treat a large amount of data. But of course, this is going to be felt more and more sensitive for us. Regarding the contribution to multi-messenger astronomy, of course, these detectors are able to receive neutrinos from the cosmos. Neutrinos are a perfect probe because they are hardly stopped by anything. So Mark already mentioned that neutrino astronomy was born actually in Japan with supernova 1987A. And the interesting thing with neutrinos is that the way supernovas collapse makes such that we receive neutrinos before we see the light from the supernova. Now, in 1987A, if I remember correctly, the neutrinos arrived about 3 hours before the light. So today we are equipped with the system of automatic warning. If a pattern resembling the one of a supernova is detected in Superkamiokande, this will generate an alert to all the other observatories in the visible, in any possible observatory using photons, and nowadays also in gravitational waves. And Hyperkamiokande will have the same role in the future.
Thank you. I'm impressed that the visual of Hyperkamiokande, it is a sci-fi-like look when I was a teenager. So can I add one question? So you said totally transparent water. The field with total transparent water. How do you realize it? How do you eliminate its contamination in the water?
There's a very sophisticated water treatment system made of several kind of filters developed by Organo, which is a specialized company in Japan. And it is, well, University of Tokyo collaborating with Organo, bringing this kind of transparency to Superkamiokande today and then tomorrow Hyperkamiokande.
Thank you. All right, so let's move on to next question. Fundamental physics demands long-term vision, doesn't it, Marco? So you are already looking ahead to the Einstein telescope, the future of gravitational wave, wave research in Europe, Italy. And with a strong tradition in this field, is proposing Sardinia as a host site, as you mentioned in the presentation. This project is backed not only by the scientific community, but also by the Italian government. Why is this investment so significant?
Well, it is significant on many levels and on many aspects. First of all, it is science. Gravitational waves are the new messenger from space, is the brand new way to look at the cosmos. We know we can learn many things with gravitational waves, but also, for example, in cooperation with neutrinos, because one of the dreams we have is to detect a supernova again. And this supernova, if we are not unlucky, will be seen with neutrinos, will be seen with photons, will be seen with gravitational waves, providing a plenty of information about a phenomena that we see. It's very spectacular, but we understand very little. So we need the new information. Gravitational waves will be part of that. But of course, there will be a new tool to look at black holes. There will be a new tool to look at neutron stars. There will be a new tool to study the cosmos in the global sense, doing cosmology in a completely independent way. So this is the first reason, the science, which is, of course, the one that drives all of us, and the curiosity and the eager to understand the world around. But of course, it's not only that, because we have a tradition, we have Virgo running, we have a strong community, we think we have the knowledge. And our government understood that and supported the idea to build the third generation detector, the one that will come in the future, hopefully not so far, in Sardinia. The reason why we propose Sardinia is purely scientific, let me say. It's not a nationalistic view, but we searched for the best place in Europe. We made a big study starting from 2005 to 2015, so 10 years of work to prepare. And Sardinia was identified as the best site for geological reason. There is a strange geological fact, because Italy, like Japan, by the way, is very seismic. We have this problem. But this is true for the mainland Italy. Sardinia is about 300 kilometers in the Mediterranean and is geologically completely decoupled. So it's not seismic at all. And the rock is very good. And we do believe we have the best site. We were able to convince our governments, let me say our governments in plural, because this is a long story. This government has completely accepted and endorsed what was done before. We have a strong support from Minister Bernini and from the government itself. Even the Prime Minister already spoke twice of Einstein telescope, which is not familiar. I mean, usually prime ministers do not speak about scientific projects, so this makes the thing very unusual and very relevant at Italian level. Of course, we have competition in Europe, so we are in the process of discussing with our European partners, because there is another candidature in the Netherlands, maybe a third in Germany, so the situation, as usual in Europe, is coming complex. But we believe we have the best site, we believe we have the community, we believe we have the strong engagement of course, of INFN, needless to say, but also of the policy and of the political makers of the region. So we really hope that Einstein telescope, ET, will be in Sardinia in some years from now, and it will be fantastic because, as I said at the beginning, it will open a completely new way of looking at the world. It's not rhetoric. It is like that. It's a completely new way to understand nature, which for sure will tell us many things that now we can't even imagine.
So you mentioned, but I also heard the Sardinia Island is best place because of the isolation, but also for the island is very hardly locked. So ground is very safe, then the seismic vibration can be very small. That is very important for the gravitational wave.
And the quality of the rock is pure granite. So even the excavation, there is no water. There are many advantages. So we are convinced that it is an excellent site to be chosen.
Well, the point of stability, noise is very relevant. He just told me a few minutes ago, with the Hyper-Kamiokande excavations, we are not really being
Yeah, so
friendly.
I complained to the Hypercave groups that many trucks are now under construction, is going to very close to the Kagra site, and every time the truck goes, and Kagra site is very scaring about the trucks.
So you have to look for a site where there's a minimum of activity. And
Including the scientific one, yes.
excluding the scientific
I'm very
one.
glad to your construction will be finished in a month.
Yeah, gravitational wave detector do not like dynamite explosions. I mean, it's...
Thank you. Okay, so I'd like to ask Hisaaki-san Shinkai-san about Japanese contribution to Einstein telescope. So thanks to the experience gained in Kagura, you've developed significant expertise in many technological fields, such as cryogenics. Yeah.
So cryogenic is a key technology, we believe. And we are going to the more than the 20 Kelvin, which is minus 250 degrees. And we know how to cool down the system because we could not use pumps. We need more another techniques because pumps using the vibrations. So we need to extract the temperature itself with the induction method. And so we use the artificial sapphire with a 20 kilogram large beak. And sapphire is best material for getting such kind of low temperature systems. And also we have know-how how to cool down. If you go into the, say, 100 Kelvin directly, then the mirror can be frosted because the incompleteness of the vacuum will make a trouble. So we need to go to the cooling down and warm up, cooling down, warm up. Such kind of technology should be developed. We can share such kind of the knowledge to the Einstein telescope groups. So such kind of science collaboration will be in plan.
Oh, yes. So additionally, last year, Italy and Japan launched a scientific and technical collaboration. I think you mentioned it. No?
For
Sorry.
Kagra and the Einstein Telescope Group had a MOA 6 years
Oh,
ago.
yes.
Yeah.
Yeah.
And our researchers group are already making the tight communications each other, and we are exchanging our idea and our results. And maybe the last year at the government level, Japan and Italy had some MOA or something.
And let me add that very recently, a year ago, an agreement between the Italian government and the Japanese government was signed for cooperation in science. And one of the two items chosen was the gravitational waves. So there is a small project, but very relevant because it brings together scientists from the Japanese community and the INFN community to work together toward new technologies, especially using the very precious and important experience made by Japanese colleagues because they are the first to try to cool down the mirrors. It seems a trivial thing, but it's not at all. It's a very tricky and difficult problem to address. They are fighting the battle now and we will have to learn how to fight the same battle in ET. So cooperation is the key because, let me say, when it comes to major top-level infrastructures, nobody can work alone. I mean, you do need the knowledge, the expertise of so many people that you have to put the community at work and not a single country or a single institute or a single whatever. We have to work together. This is the key of success.
Yeah, on the same line, this makes me think that and you showed KM3net. So this kind of cross-contamination between collaborations apparently working independently happened already in Hyperkamiokande, because the composite photon detector is a technology first developed for KM3net. So with due modifications, but the basic idea is the same, this came to Hyperkamiokande. So this happens and it's extremely useful.
Do you have some comments? That's okay? Yeah.
No, I can just complement it. Yes, I was thinking while he was speaking that the PMTs that now, these composite PMTs that now HyperK has adopted were actually developed in Napoli for the KM3net collaboration some years ago, and we contributed, is one of our contributions to HyperK, and of course we are very happy and proud of that.
Very interesting. So I'd like to discuss cultural exchange over scientific collaboration between Japan and Italy. So just as a Japanese experience with Kagura is important for the Einstein telescope, the expertise developed by the Italian scientific community is building detectors also contributes to significantly to Hyperkamiokande. These collaborations are not only valuable for research activities, but they also help to bring scientific communities and, in the long term, different cultures closer together. So could you explain your view on cultural exchange through scientific collaboration between Japan and Italy?
It's to me? Or to
first.
anyone?
Whoever wants to comment on this.
I think that science is also a tool for diplomacy, let me say. In the case of Italy and Japan, who are close friends, it's done to exchange information, to exchange knowledge, to exchange human expertise at many levels. Of course, we do contribute to several activities in Japan. Sandra mentioned Bell 2, but of course we have been a part of T2K and Super K for a while, and more recently, of course, we are joining Hyperkamiokande. So we are happy to collaborate, but it's beyond the simple, sharing of cost or sharing of effort. It's really exchange of people, exchange of cultural approach. People know each other, learn different approaches, attitudes, features, virtues, defects. Everything is shared, and I think at the end this is good for the society and for everybody, not only for science. But focusing on science, it is key on science today, because the complexity, the difficulty, the cost, the length of the project. Now we are familiar with projects that are thought, designed, built, and operated in decades, not years. And this requires a community, requires the fact that the information is also passed from the father to the sons, if you let me say this word. The people that design is not the same that builds, and is not the same that operates, because the time span becomes very long. So the fact that we are a community, the fact that we work together trying to subdivide the effort and sharing the ideas is the key. of the success of the big infrastructures and of the big scientific endeavors.
Yeah, if I may add, I think that not many of our colleagues do realize that working in large collaborations like these, they're actually doing scientific diplomacy. But it's true. I mean, fundamental science is by its own nature open. So you can't do it if results are not open, if ideas are not exchanged, and if borders are not, if not eliminated, at least opened as far as possible. And is also the reason why also historically science has played an important role in approaching communities, even, let me say, between countries whose basic political understanding was not as close as the understanding about basic science. So it's a long-term thing which may bring good to societies. We difficult to see now what and when, but it does happen. I mean, the past has taught us that it does happen.
I'm one of the person of the leading group of the outreach of the gravitational wave researches between LIGO, Virgo, and Kagra. And every time I feel the difference of the cultures, that for the scientists, we use the same purposes to detect gravitational wave and announcing the new results and what is interesting, what is new, what is going to do. But in Japan, actually, Kagra is very sensitive status now because we are still waiting for the first detections. So our funding agency is very sensitive to announcing to everything from Kagra. And I'm very feeling frustrating every time. For example, our funding agency says, don't get people misunderstood. That is the primary issue. So we cannot make the announcement what is interesting now until when we actually make our observations. So maybe within a year, Kagra will have one detection or two second detection. Then we can celebrate to announce everything. But the European people or Americans are eager to have many times in announcement, and I'm always enjoying such kind of the outreach activities. And such kind of the activities are highly advanced than Japan, and I'm always running a lot. So for the some visualizations or movies or some many materials, we are now sharing each other. That is really helpful. And I'm now still learning about how to approach to the general people. And European or Americans are our teachers still. That is, I'm feeling the difference of the culture.
Very interesting. So in culture, in the sense of culture, a designer once said to me, so he said, difference makes a difference. So what difference do you find in attitude toward science between Italy and Japan?
Attitudes. Okay. Well, people want to know the new physics, new astronomy, but now the science is very big. Big science requires budget. So, as I thought, so science communication techniques are very key to access to the general people. So such kind of attitude or some movement are really necessary for us. That I'm feeling.
But instead of the difference, I would focus on what it is in common because I think it is important. Of course, if you look at Japan and Italy in general, they are two very far away countries, very old, with a very long history, and of course very different on many things. But even assuming that, which is of course true, when you go to science, the difference fades away. And why this? I think there is a reason. because science is the activity of investigating the real world, and the real world is the same for everybody. If you accept the scientific method, you immediately not become equal because we like different dressing, different food, different many things. But if we discuss about the fact that neutrinos have a mass or not, we have a way to discuss and a way to agree and finally reach the same conclusion. Science is a strong driver of diplomacy because for many reasons maybe, but the main one in my opinion is the fact that we accept honestly to investigate nature, and it is the same nature. The laws of physics are the same in Japan and Italy. That's a clear statement. And it's less trivial than it looks, because of course we see the world, especially today, extremely conflicting, debating very stupidly, let me say, very often in ways that are harder to understand. The scientific approach protects us from that, and it's very important that we stick on the cooperation mode. Last comment, competition is important. We all like competitions. Scientists like to compete, but I think that the competition should not be never so strong to hide the cooperation, because the cooperation is more important, and probably too much competition hurts science. We have, yes, competition helps, is a push, so in this sense is positive, but the collaboration mode, in my opinion, is the key for the big enterprise we have to do in a moment in which money is lacking, because it's not easy to find resources anywhere, and we have to stick together, to work together as much as possible, especially on the big infrastructure that are the main items of these conversations, and the big infrastructures requires the collaboration of everybody.
You use the word debate, but as a science, so the nature will give us the final answer. So just we are discussing about how to understand easily or simply. Such kind of things is the scientist. So we don't use a debate, we are discussing.
Well, from my own point of view in the collaboration, I do see cultural differences, which I tend to interpret as a richness in the collaboration. I know that people coming from different places in the world, for example, react in a different way in front of problems, right? Well, science at a certain point makes such that the feeling of the people is that the problem has to be solved and the common ground is found. And this is usually maybe a difficult passage for a collaboration, but after that, the collaboration becomes stronger, and this is maybe true also for societies, right? So I wouldn't consider cultural differences as something bad. It's a richness, and it's.
But I heard you were visiting Japan many times as a hyper-gay. You have a cultural shock in Japan? Did you have?
Actually, I did not,
Oh,
I must
okay.
admit. First time I came to Japan was 1993. I honestly did not have a shock. I mean, of course, I mean, you land in a place where, for example, you can't read everything you see, you can't speak the language, but I mean, somehow I found myself feeling good. I mean, I had a very, very positive impression since the beginning. So I'm not the one who is going to tell you, no, I'm scared going to a different country. I mean,
Glad to hear that.
No.
Okay, can I add one more question to this brilliant discussion. So what can be done to support and promote the growth of research infrastructures, scientific collaborations, and more broadly, the recognition of the value of big science? Anyone?
What can be done? Many things. I think, first of all, explain that the money put in big research infrastructure is not spent, but is very wisely used. There are data that says that the economic return of investments in big research infrastructure is very good. It's typically higher than many other investments. Ezio was mentioning at lunch a number that there is a study that says that for every euro put at CERN, the economic return in Europe is 3 euros, okay? Yes. Of course, it's not easy to explain, also because the economic return does not come tomorrow or in a very short time scale. It arrives usually on a long range, and the politicians do not like the long range because they want to be re-elected, so they want the results that come immediately. But sometimes, not very often, but sometimes there are wise politicians, and we have to work in that direction because the investment is a good return also if you don't care about the science or if you don't care about the pure curiosity-driven approach of studying the universe. Even if you care only about social and economic return, the large infrastructure are a good investment, and I have to say, and I'm happy to say that this government in Italy has understood this very well, because there is a clear consensus on ET, and part of this comes from the fact that they acknowledge that in case ET comes to Sardinia, this will be a big and important economic driver to Sardinia. And the same argument can be used for the future FCC at CERN. I mean, there is a fundamental and crucial laboratory which has made a lot of science, is doing a lot of science, but it's very important that he has a bright future, and a bright future for CERN can come only from a big investment on a new machine. And on this, INFN, of course, but also the government has cleared this message. We have to think about the future, and we have to look ahead with a new endeavor at CERN and in Sardinia. I'm thinking of these two experiments because they are the two hot ones. But of course, the principle, your question, it was more in general, and there is no such a bad experience in large research infrastructure. Every time you do one, there are beneficial effects around, and not only around, that are clear. Gran Sasso is another example. I mean, the area around Gran Sasso has changed a lot in the last 30 years, also thanks to the lab and all the activity driven by the lab. So we do have evidence that this is true. It's not just an opinion. There is data.
Okay, I would like to mention about a more concrete one sample in the near future, 5-10 year scale, on the gravitational wave physics and astronomy. So currently, in this our observation from 2 years ago, we have detected 200 gravitational waves, and every time, rate is something once in 3 days or something. Every time we catch the gravitational wave, we announce to the result of the we detected. So we sent out a circular to the all over astronomers in the world. That is normally within 20 or 30 minutes. Then after receiving such kind of circular alert, then all the astronomers in the world will try to search the follow-up observations. But we were expecting maybe within this year or maybe in the 5 years, we can announce the existence of such kind of gravitational wave before catching it, because we can search the gravitational wave before merger, maybe 1 minute before the merger. Then we can send out the alert to the all astronomers in the world, and maybe astronomers will be prepared for the telescope, or any other neutrino researchers will prepare for the catching the neutrinos, and we will simultaneously can catch the event of a supernova explosion, or also the neutron star mergers. So such kind of exciting event can be announced, I believe, within 5 years. So there are many young generation people here, and that's your turn to do such kind of physics and astronomy. That's a very near future and predictable result.
Regarding impact on the communities, we are going to have some. You have to imagine that in 2027, Hypercamiocandia will start the final phase of construction, which will require about 100 people on site in a small town like Kamioka. So we will be noticed and we will bring additional activity there. And already preparing for that is a challenge for the local community working on this together with the University of Tokyo. So it's true, these kind of projects do have an impact on people where those projects are located. And usually long-term impact, because then you don't come back. I mean, once the toothpaste is out of the tube, it doesn't go back.
Okay, so we close this session with this beautiful and brilliant discussion. Thank you so much.
Thank you.